Hello, welcome to lecture 4 of Symmetries, Particles and Fields. So in this lecture, we're going to take these group manifolds. We've just seen in the end of the last lecture the group manifold for SO3, which is this ball in R cubed, but with antipodal points on the surface identified. So we want to talk about group manifolds more generally. So we're going to set up a coordinate system on them. And then we'll look at differential group transformations around the identity element, which of course is now going to be a point on this group manifold. And those differential group changes will lead to the introduction of the concept of a Lie algebra. And as you've probably gathered, Lie algebras are important for analyzing what's happening in terms of Lie groups. Okay. So here we have parameterization. Of the group manifold. So let's choose some coordinates. So I'm going to call a point X, but this is really going to be a vector in our Rn. So these are on our manifold G. So a Lie group element then depends on which point of the manifold you're on. In fact, it's parameterized by the point of the manifold. So we write the group element as G, depends on this point X, and this is in the group. So different points correspond to different group elements. Different points X, Y, Z correspond to different group elements. So we have the fact that the group must close under group composition. So closure of the group is written as, so the group element corresponding to Z must be equal to G of X, G of Y, where all of these are different points on the manifold. And now the coordinates, the individual coordinates of this Z, the individual components of the coordinate Z must be smooth functions of X and Y. So the rth component of Z is some smooth function of X and Y. So let's call this, I'm going to call it phi. So phi has R components as well, and it's a function of the points, the coordinates of X and Y. So here we choose the origin of our coordinate system to be the identity. So G of naught is the identity E. So what this means is, because we know from the group axioms how the identity acts on other group members, so that we know that what the function is where one of the arguments is 0, we just get the component of the coordinate back no matter which side that's on, and this is equation 2.1 for the label. So, all right, so these relations mean that we can expand phi of r in terms of 2 points, x and y. So this is a Taylor expansion. And again, this is an exercise. And you can write phi r of x and y in general as xr plus yr plus some constants, CRST, times XSYT, plus terms of higher order, so x squared y terms and y squared x, etc. Now, it's not immediately obvious that you can do this. For example, I've got no x squared terms and no y squared terms there. And so the exercise will take you through how to prove that this is the general expansion around small parameters x and y. So these CRST, these are just numerical coefficients in the expansion. Okay, what about inverse elements? Well, I'm going to call the coordinates of the inverse elements as the same thing, but with a bar. And so, our group axioms imply that the function phi of x bar and x is same as the function of x and x bar, and it's got to be 0. Okay, so this is 2.2. So again, from an exercise in the book, you will get that. So see exercise, x bar is minus xr plus CRST xSXT plus order x cubed terms. So actually these numerical coefficients that have appeared, these CRST, they're important. And in fact, it's really them that determine the possible Lie groups. And we'll see this later. Next lecture. So actually, it's some other objects, which is CRST minus CRTS. So it's anti-symmetrized in the lower two indices. So these determine the possible Lie groups. Now we have this other condition, this other group axiom that must be satisfied, and that's associativity. And so in this language, associativity reads that phi r of x and phi of y and z is equal to phi r of phi of x and y comma z. This is equation 2.3. And actually, so it's these numerical coefficients which also satisfy this associativity condition, which will determine the possible Lie groups. Okay, so now let's go on to Lie algebras. We want to look near the identity and see how the Lie group is defined near that. Okay. So the Lie algebra of a group G. So we write this L of G. I should say a Lie group. Is defined on the tangent space. To the group manifold G at the identity E. Okay, so L of G, you'll see sometimes seen written usually in terms of printed text. Instead of L of G, sometimes they use a lowercase fractal script letter version of the group. So a rough approximation, fractal split script looks quite spiky. So it would be a lowercase g in this spiky script. But because I'm handwriting things and it's difficult to write fractal script, we're going to stick to this L of G notation. All right, let's define this tangent space. The tangent space to G at E, which is what we need, denoted. Oh, sorry. Let's define a tangent space at a generic point, and then it'll be the Lie algebra will be defined as a tangent space at the identity. So this is denoted T suffix P of the group G. So this is the dimension G dimensional vector space spanned by the differential operators. And I'll give you those in a second. So these differential operators are the set of partial derivatives with respect to the coordinates. And J, of course, goes from 1 to up to dimension G. Okay, so we can draw a picture of our group manifold. I'm just going to draw some sphere or something, but it could have a different shape. So let's draw our group manifold. So that the idea is that this is G. We have our point P. And the idea is, so we have a plane tangent to this point, which I'm going to try and represent like that. So let's suppose we have some function f on our group manifold. So this function takes a point on the group manifold and maps it to a real number. So this is a function on the group manifold G, and let some big X, which is defined to be xi d by dxi, be in this tangent space. So the action of our of X on our function f is defined to be xf equals xi d by dxi df dxi at x equals the point P. Now let's consider some smooth curve on P passing through this point. Okay, so we've got some smooth curve. I'm going to call this curve C. passes through the point P. So we're going to parameterize this curve by some parameter t. So considering a smooth curve on G. So we call this curve C, and it maps a real number to G, and this real number we're going to call T. And so this has some coordinates, each of which is a function of T. Going through the point P at t equals to 0. So in other words, what that means is xi of 0 is equal to pi. Well, the ith component of p. So we can then associate a tangent vector at p. So let's call this VC is dxi by dt at this point P. So that's at t equal to 0 on d by dxi. So this is in the tangent space at point P. Okay, so that defines our tangent space at point P. So if we act on some function, on our function f, so the idea is we have some function, varying over this sphere, but we take this path C at a particular point P, and then we want to act with the tangent vector on this function f. So we see that VC of f is just dxi dt at t equals to 0, d by dxi of f of x evaluated at x equal to p. All right, so this is equal to, just by the laws of differential calculus, this is the total derivative at the point t equal to 0 of f with respect to t. Okay, so remember we said that the algebra is the tangent space at the identity, and we've just defined what this tangent space is along some curve at least. So let's give some examples, because at the moment it's pretty abstract. Let's look at SO2, which you've already seen. So the Lie algebra of SO2. So here, f of t, well, remember we had cos theta minus sine theta, and cos theta parameterizing SO2. But now what if cos of theta is actually some curve C of t? And we must have that C of 0 is equal to 0 because that's the identity, that corresponds to the identity element. So this describes, so this function describes a curve in SO2 through the identity element. Okay, so now let's calculate our tangent vector at this point. Okay, so you do the derivatives and you get the following. So there's an overall factor of c dt evaluated at t equal to 0. So, all right. So if you think about it, for any curve, you're going to get some number for this derivative. Remember, everything has to be smooth functions, and so for any, so they're all going to be multiples of this matrix. So it's a multiple of 0, minus 1, 1, 0. So therefore, our Lie algebra elements of SO2 is the set of all matrices that look like this, where little c is real now. So a comment is in order. Notice that this Lie algebra isn't in the initial group, at least for c not equal to 0. So nearly all of these matrices so they aren't in SO2, they're in the algebra of SO2, the tangent space at the identity. Okay, so that's our first example. And now we're going to do something that's more general. We're going to look at the Lie algebra of SON now. So now we consider a curve. If we follow the same kind of logic, we're going to have some matrix, which is a function of t. So this has to be in SON. And the matrix at t equal to 0 has to be the identity matrix, which is the identity element, mapped to the identity element. So we have this constraint. What we want to do is find out what the derivative of this matrix is at t equal to 0. And that will tell us the Lie algebra. But we notice there's a constraint here because if we take the derivative of m transposed of t times m of t, okay, because these are in SON, this is d by dt of the identity matrix, which is a 0 matrix. Okay, so evaluating the left-hand side, this is equal to m transpose m dot plus m dot transposed m for all t, where m dot here is just the time derivative. So a dot is the time derivative. And at t equals to 0, remember, we have the matrix is equal to I. Well, anyway, I've said that. So, oh yeah, sorry. So if we look at this equation at t equal to 0, then we have that the matrix and its transpose is equal to the identity. Then we have the m dot at t equal to 0 is minus m dot at t equal to transposed at t equal to 0. So remember, it's these derivative matrices we're after for the Lie algebra, but we've just proved that they're anti-symmetric. So the Lie algebra of SON is the set of all matrices which are anti-symmetric, n by n matrices which are anti-symmetric. So it's the vector space of real antisymmetric n by n matrices. Okay, so let's count the dimension of this Lie algebra. Well, we start with an n by n matrix for this Lie algebra with some constraints, and it's the antisymmetric constraint. So we start with n squared. Now, if you think about an antisymmetric matrix, its elements down the diagonal have to be 0. Because they have to be equal to minus themselves. So we subtract n. And then we've got off-diagonal elements, but all the ones underneath the diagonal are just minus the ones on the top. So we divide by 2. So that's the dimensionality of the Lie algebra of SON. And we make another comment here. Because you can ask, well, what's the Lie algebra of ON? But actually, it's the same thing as the Lie algebra of SON, because near the identity, a member of ON has determinant +1, not -1. So all of those elements of ON which involve a reflection are not near the identity. Okay, now let's look at the Lie algebra of SUN as our third example. Okay, so now MT is a curve in SUN. Again, with M of 0 equals the identity matrix. Now we're going to assume an expansion. Remember, M of T is, everything's smooth here. So let's assume a Taylor expansion in small t. So what I've got here is some matrix Z of numbers, complex numbers, I should say. Okay, and here our constraint is that M dagger M has to be the identity. That's the SUN constraint. One of them anyway, it's the UN constraint actually. So if you substitute M of T into this and look to first order in T, you'll find that this matrix Z is anti-Hermitian. Okay, so expanding U of T, sorry, M of T. If we just look at and see what this is so I'm not going to, I mean, we just take into account the fact that Z is anti-Hermitian here. I could have written this as a Z12 dagger, Z12 star, but I'm not going to. So that's our matrix. And plus higher orders, I should say. So our determinant, yeah, sorry, we know this is true. So an anti-Hermitian matrix has zeros along the diagonal. That's why we have no Z11s we just have a 1 on the diagonal. So the determinant of this matrix, well, we're going to get lots of terms, but what I'm going to be interested in is only picking up the first order term. And there's going to be plenty in the diagonal. And all of the other ones involving off-diagonal elements are going to be 1 order higher in T. So if I, again, only take out the first order terms here, I get 1 plus T times the trace of Z plus order T squared. Okay, so the fact that it's a special unitary matrix means that det U, the determinant of M is 1. For all T. So this implies that trace of this matrix Z must be 0. So we have 2 constraints. We have anti-Hermitian and so it's the set of n by n traceless anti-Hermitian matrices. Because again, if we take the derivative of this this M with respect to T, in the first order terms, we get this traceless matrix, anti-Hermitian matrix. So, okay, good. Those are our examples finished. So let's make another definition. We can define a Lie algebra algebraically. I can do that now. So a Lie algebra so is a vector space over a field F. And it's equipped with a Lie bracket. And we're going to write the Lie bracket like we would some commutator. So it's square brackets with a comma in it. And what this does is it maps from 2 Lie algebras of some corresponding to some group elements to a single Lie algebra of the group elements, such that 3 conditions are met. Firstly, this Lie bracket. So if we take 2 elements in the Lie bracket X and Y, must be minus the Lie bracket of Y and X. So in other words, this is anti-symmetry. Secondly, we have the linearity condition. So if we take 2 numbers alpha and beta in the field, alpha X plus beta Y Z is alpha X comma Z plus beta Y comma Z. So these are in F. Alpha and beta are in F. X, Y, and Z are in the vector space. Okay, so this is linearity. And thirdly, we have the Jacobi identity, which written in terms of Lie algebras is the following. So here, X and Y and Z, etc., are written as XA, TA, where A are just the different coordinates, or we can write them as I's actually. And the T, I, this T is in this tangent space at the point, well, actually, at the identity. So these xi's, these are parameters. So we've got to map from, so we mapped from this bracket to one element of the Lie algebra. And an element of the, this X is one element of the Lie algebra. So what we need is that this bracket XA, so TA, Y, B, T, C, TB. So this has got to be equal to some other point in the Lie algebra. So let's call that ZC, TC. So the question we're going to set about answering now, although we won't finish it this lecture, I don't think, is what is Z's, what's this coordinate Z as a function of the coordinates XA and YB. I've switched from I's to A's and B's here, but it doesn't matter. They're all the same index. So we'll now find it with some effort, and we won't finish it this lecture, I don't think. All right. Consider a group element close to the identity g of theta, and theta is going to be an infinitesimal coordinate in infinitesimal components. So we have g of theta, and theta is infinitesimal. That's why it's close to the identity. So it's gonna, this g of theta is going to make an infinitesimal change in an arbitrary group element. We'll just call this arbitrary group element g of z. Z is not necessarily infinitesimal. In fact, it's not in general. And what we want to know is how z changes when we apply on the right this g of theta. Okay, so we can use, we know how to take these group products. It's just, what happens is that the coordinate z just ends up being our function phi of z and theta. And so theta is infinitesimal, so we can expand this right-hand side around small theta, do a Taylor expansion. So we get that dzr is theta a, d phi r, z of theta by d theta a. So yeah, that's just what we derive from the previous equation. Now, this d phi r by d theta a evaluated at theta equal to 0, that's going to be some, if we consider r and a to be rows and columns, this is just some matrix of numerical coefficients. Mu, so I'm going to call it mu, and then we've got rows and columns, a and r, but it does depend on z still. Okay, so we have this, we just defined that, so we have dzr is theta a mu a r z. Okay, this is equation 2.4. I'm numbering the equations that we need to refer to in the future. Okay, all right, so that's how we start off. Now we consider the group action on the tangent space. So we take a group multiplication rule. So gz is gx, gy, but we fix gx. We consider this to be a fixed group element. But we let this one, let g of y, be infinitesimally changed. So in other words, we want to know now what happens to z differentially when y changes a little bit. So remember, okay, so this is going to be from above, this is equal to gz g theta. All right, so we just use the above equation again, and we have here that dy r, the rth component dy, is theta a mu a r of y. So this implies, so if I can consider this mu as a matrix, I can multiply by the matrix inverse. So lambda, this matrix lambda y is the matrix inverse of mu of y. So writing it out in components, we have that lambda a r y equals mu r b y, and it's of course delta a b, where this delta is just Kronecker delta, 0 if a not equal to b, but 1 if a equal to b. All right, so now we substitute to find that dzr is theta a mu a r z, remember. So now we substitute into that and for mu, and we find that this is dy s lambda s a y mu r a of z. So now we take the derivative with respect to ys, and we've got lambda s a y mu a r of z. So I'm going to call this 2.4b. So note here that phi r of 0 and theta is theta r plus some higher order terms. This implies that mu as at 0 is going to be this Kronecker delta plus some higher order terms. Okay, so our tangent space coordinate TA of y, this is equal to mu a s of y. So we're going to define this here. It's this matrix times d by dys. So this is equal to the matrix dzr by dys, d by dzr. And by 2.4b, this is equal to TA of z. So we just substitute 2.4b in for this middle factor, and we get TA of z. So, all right, these are vector fields. The vector field, these are a basis, and they're called left invariant vector fields. They're called left invariant because we were considering group, they're invariant under group transformations by the action of the group on the left-hand side. And they're belonging to the tangent space of the group, since they're invariant under group transformations, which look like g of y goes to g of z equals g of x, g of y. Okay, so we're getting to an algebraically heavy section of the course. Don't be surprised if you have to spend some serious amount of time going through this in your own time and working out where everything fits. I reckon for the harder courses in part 3 of the Mathematical Tripos at the University of Cambridge, a lecture often will take even the best students a day to properly work through and work out all the ramifications and make the connections and so on. So the vector space, I'm going to make a statement now. We're going to prove it next time. I think I'm running out of time. So the vector space spanned by the Lie algebra so this is the set of theta A TAs. So in other words, in fact, let's not call that theta. Let's call it X A T A. In other words, constant linear combinations of these T's. This is closed under taking the Lie bracket. For any two vectors which belong to the Lie algebra. And it defines the Lie algebra. So we're going to go on to show this. Again, it's going to be a bit algebraically heavy. We'll get into it at the start of next lecture, and we'll derive the defining relation of the algebra, and at the same time we'll answer this question of what are the coordinates given by what are these coordinates ZC? Where did we have it? Here. In terms of the initial coordinates. So what are the coordinates of the Lie algebra in terms of the initial ones? Then next time we're going to look more closely at the relationship between the Lie group and the Lie algebra. Thank you.